Welcome viewers, in this video we will see the solved problem based on the slip of the 3-phase induction motor part 4. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive, link is given in the description box. Now we will go to the problem. A 3-phase 4-pole 50 Hz induction motor has slip ring rotor. So this coming under the slip ring rotor. The rotor winding is star connected with 0.2 ohm of resistance per phase and standstill reactance of 1 ohm per phase. Its open circuit EMF between slip ring is 120 voltage. When stator is excited by the rated voltage, its full load speed is 1440 rpm. Find the rotor current at and rotor power factor at starting as well as full load. We need to find the two parameter, rotor current at the corresponding rotor power factor for starting condition as well as the full load condition. Now we will analyze the data. What are the data available in this given problem? The number of poles is 4. Poles is given as 4. The frequency of the supply system is 50 Hz. R2 and X2. This R2 refers rotor, R1 refers stator. The rotor data are given. Resistance is 0.2 ohm and reactance, standstill reactance is 1 ohm. And E2 is given 120 voltage. This E2 also refers the rotor, 120 voltage, line voltage. In case of phase voltage, this 120 divided by root 3, 69.282 voltage. And the speed is given 1440 rpm. Now we need to find the rotor current during the starting as well as full load. During starting we can use the normal formula. During the full load we need to consider the slip of the induction motor. Now we will find the rotor current at the starting condition. So I2 equal to E2 divided by Z2, the general formula. The current equal to voltage divided by impedance, that is E2 divided by impedance is the sum of resistance and reactance of the rotor. 2 refers rotor. So the rotor voltage divided by rotor impedance R2 plus jx2. So this R2 plus jx2 is written as square root of R2 square plus x2 square magnitude, right. So all these data are available. E2 is 69.282. E2 given as 120 voltage, line voltage, this one phase voltage, and the resistor value given 0.2 ohm, reactance given as 1 ohm. So all the data are available. So by simplifying this, what we got, 67.934 ampere. The rotor current at the starting is 67.934 ampere. Now we will find the rotor current at the full load condition. For a full load means definitely we need the value of slip of the induction motor. So in order to find the slip of the induction motor, first we will find the synchronous speed. Synchronous speed equal ns equal to 120 f by p, very standard formula. Number of 120 into frequency divided by number of poles. These two data are available. 120 into the frequency given 50, number of poles is 4. So 120 into 50 divided by 4, what we got, 1500 rpm. So the synchronous speed of the induction motor is 1500 rpm. So from this we can able to find the slip of the induction motor. S equal to ns minus n divided by ns. Synchronous speed minus rotor speed divided by synchronous speed. See, the speed is n is already given, 1440. Synchronous speed we calculated. So 1500 minus 1440 divided by 1500, it is 0.04. The slip of the induction motor is 0.04, that is 4%. Right? For a full load, definitely we need the value of slip of the induction motor. Then only we can find the full load parameters. So I2R equal to E2R divided by Z2R. Previously I2 equal to E2 by Z2. During running condition it is given I2R, R refers the running condition, E2R, EMF under the running condition, impedance also under the running condition. How will you find E2R? E2R is nothing but S into E2. the EMF in the rotor under running condition is slip into rotor EMF under the starting condition, S into E2. Similarly, Z2R is nothing but square root of R2 square plus S into X2 square. Because R2 is constant, the reactance will vary with the slip of the induction motor. So, S into X2 square, right. So, this I2 refers under the starting condition, I2R refers the running condition, that is based on this SE2 divided by square root of R2 square plus S into X2 square. So, here we are referring the slip of the induction motor. Now, all this data is available, we can substitute. I2R equal to 0.04 into the slip of the induction motor is 0.04 and E2 what we calculated 69.28 divided by resistance given as 0.2 and slip is 0.04 into reactance is 1. So, by simplifying this we got 13.586 ampere. So, the rotor current at the full load is 13.586 ampere. Now, we need to find the power factor for this corresponding rotor current during starting as well as the running condition, full load condition. First, we will find the rotor power factor at the starting condition. Very simple formula, cos phi 2 equal to R2 by Z2. The power factor, one simple formula is available, resistance divided by impedance, R2 divided by Z2. So, R2 divided by Z2 is nothing but square root of R2 square plus X2 square, resistance plus and reactance. So, that we will get the impedance. So, these values are already available, R2 is 0.2 square divided by the reactance is 1 square, right. So, by simplifying what we got 0.196, power factor is cos pi 2 is 0.196 lagging, because of the inductor we are put it as lagging. Now, we will find the power factor at the full load. The full load mean we need to refer the value of the slip of the induction motor. The same formula cos pi 2R. Cos pi 2 refers the standstill condition, cos pi 2R, R refers the running condition, R2 divided by Z2. This R2 is constant, it will not vary with the slip of the induction motor, so it is taken as it is. But Z2, resistance plus reactance, this reactance is based on the slip of the induction motor. When the slip changes, the reactance also changes. So, S into X2. So, that is R2 divided by this R2 plus JXX2, complex number can be written in the magnitude, square root of R2 square plus S into X2 square. So, all these values are available, we can substitute the values. R2 value is 0.2, this 0.2 square plus the slip of the induction motor is 0.04 into X2 is 1 ohm. So, by simplifying this what we got 0.9805 lagging, because of the inductor it is given as lagging. So, in this problem we calculated the rotor current under starting condition as well as running condition, then corresponding power factor at starting condition and running condition. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Thank you for listening.